Now, if I'm given a circuit which I marked in this block as complex network, and this is my resistor, and you are told to find the current in this load resistor. Okay, that is what you are asked, to find the current in this load resistor. Now this complex network is a combination of resistors. The combination can be series, parallel, star, delta, or any kind of combination which can include energy sources. Okay, this is the combination that is involved over here. Now, if I want to use the technique of Norton's theorem, what I need to do is, this entire complex network, what is mentioned, okay, I have to replace it by this dotted block. This block that is there, okay, I have to replace this entire network by this dotted block. This dotted block contains a current source, this is a current source, and a resistance Rn, both of which are in parallel. So complex network you are replacing with this, and this block is called as a Norton's equivalent circuit. Now, the same load resistor which is there over here, you put it over here, fine. And what do you do ultimately is, you will find the current over here. So when I am using my Norton's theorem, please understand, except my load resistor, okay, if I separate it out, except my load resistor, the entire complex network has to be replaced by a Norton's equivalent circuit, and put this load resistor back over here. Now in this circuit, I will calculate my current. Please note that the value of this current and this current has to match in your theoretical calculation as well as your practical calculations. So, even if I mount this practically, my original circuit, connect an ammeter over here, match the current, connect my Norton's equivalent circuit on the breadboard and match the current by using an ammeter over here. Both these currents have to have the same value in your theoretical calculation as well as your practical reading. So that is why you can substitute a complex network by a resultant Norton's equivalent network. Next, we have to see is how to reduce this complex network to my Norton's equivalent circuit. So your job is to find this Norton's equivalent circuit. Now, supposing this is the circuit given to you, you have to find the current in this particular load resistor using Norton's theorem. Okay. So what is your job is, the entire network, okay, which is separated by this green line, the network line to the left of AB, has to be replaced by a Norton's equivalent circuit as shown in figure 4. So this network which is there, this entire network has to be redrawn into this form, a current source and a resistance in parallel. This is my original network, this is my Norton's equivalent circuit. So how do I go about reducing this network to this network? Okay, now what is happening is, how to get this network to this network. Step 1, we will discuss how to find current. Okay, this IN, how to calculate will be this as my step 1. So what do you do in step 1 is, this network to my left, I keep it the same over here, okay. I have to remove my load resistor RL, and instead of that I have to place a short across my points AB. Okay. Across my points AB I have to place a short, and I have to calculate calculate the current in this short. Okay. Now, how to calculate the current in this short, okay, is my next step. Once I find the current over here, its value in the short, this current value has to come over here. Now to find this current, how do I go about it is, if you notice this current IN is the current over here, and this current is a current, part of the current coming from my source. So if I have a look at this circuit over here, circuit 2, the current I is coming from the source to this junction. At this junction, it is dividing itself into two parts. One part is flowing through R3, the other part is flowing through R2. The part of current that is flowing through R2 is called as IN, okay? And you have to calculate the value of current IN. Now, to find IN, you will have to know the current I, because the current I, if you notice, is dividing into two parts. One is flowing through R3. See, let me call it as I1, okay? And one that is flowing through R2, it is IN, okay? You have to calculate this value of current of R2, which is IN. And this IN is a part of my main current I. I can calculate IN using my current divider rule. Okay, I'll calculate using current divider rule. And I have to calculate, because if I have to apply current divider rule over here, I will have to know my source current, which is providing me IN. And to find current, I will use Ohm's law. So these are the steps by which I will find that current of IN over here. Now to find RN, as my next step is to find RN. So this is the circuit to find RN over here, okay. Now to find RN across these terminals AB, these are my terminals AB to find RN. What I do is, I have to remove my load resistor. So if you check, load resistor is not present, load resistor is removed. Also in this entire circuit which is there to my left, you have to remove all the energy sources. Here I have one energy source, which is a voltage source. It is connected across these 2 points, okay. So since it's a voltage source, I have shorted it. So after imposing these 2 conditions on the circuit to find my Norton's equivalent circuit for resistance, this is the circuit which I'm going to use to find Rn. That value of Rn, I will put it up over here. Okay. Now your job will be to find the value of effective resistance across these 2 points AB for this particular circuit. Once I get the value of Rn, I will put it over here. This will be my Norton equivalent circuit. Place back my load resistor. Your job is to find what is IL, okay, the Norton's current flowing through this load resistor, the actual current, that's the current of my load. How will I find it is, if you notice, this current I is dividing into 2 parts. One is through RL and one is through load RL. So since this current is dividing into 2 parts and you know your main current already, to find IL you will use current divider rule. Okay.